Okay, welcome to this explainer. Today we are diving into a topic that honestly feels like it was ripped straight out of a sci-fi movie, brain-computer interfaces, or BCIs for short. We're going to look closely at the science, the absolute boom in the industry right now, and, the profound ethical questions that pop up when you link a human brain directly to a machine. There's a lot of ground to cover, so let's get right into it and figure out exactly what's happening in this space. Right off the bat, let's just address the elephant in the room. When most of us hear about neural implants or brain-machine connections, we instantly picture those crazy movies where machines are, like, downloading our deepest secrets. So, the big question, are computers finally ready to read our minds? It's kind of a terrifying thought, right? Well, let's dive into this. So that whole mind-reading thing, it's a huge myth. A BCI absolutely does not, and literally cannot, just extract thoughts from an unsuspecting person. The actual scientific reality is so much more about cooperation. A BCI needs the user to intentionally generate specific brain signals that represent a goal. It's like a dance. After a period of training, the system learns to recognize your specific brain patterns, and you learn how to produce them. It's a true partnership between human intention and machine recognition. Here's our roadmap for today. We'll start with the computing catch-up, define what a BCI actually is, look at how they work, check out the market and innovators, and finally wrap up with ethics and why this is a last resort. All right, part 1, the computing catch-up. Why is this all happening right now? For decades, computers just weren't powerful enough to handle the sheer complexity of the human brain. The neuroscience itself actually isn't brand new. Researchers were looking into brain-computer interfaces way back in the 1970s. They could observe the signals back then, but translating those incredibly intricate signals into digital data, we just didn't have the computational horsepower. But then, as processing power and storage exploded in the 2000s, life scientists finally got the tools they needed. And today, high-performance AI is literally unlocking that complex neural data in real time. Moving on to part 2, defining the BCI. And the crucial point here is that we have to set some really strict boundaries. So what exactly are we talking about when we say BCI? Well, a brain-computer interface is a computer-based system that acquires brain signals, analyzes them, and translates them into commands that control an external device. Think about it. Normally, your brain sends instructions down through your peripheral nerves to your muscles, which lets you speak or, walk across a room. A BCI bypasses that whole system. It uses the brain signals themselves as the direct source of control to operate software, a robotic arm, or a medical assistive device. Because we're being so strict with this definition, a true BCI has to measure signals originating straight from the central nervous system. This means we have to be super clear about what does not qualify. Voice-activated assistants? Not a BCI. Systems that detect muscle movement? Also not a BCI, because they rely on those peripheral nerves. Even a standalone EEG recording system doesn't qualify on its own. While an EEG captures brain signals, it just records them. To be a true BCI, the system has to interpret those signals and convert them into actions that actually affect the user's environment. Okay, part 3, how BCIs actually work. Let's look at the mechanics, and what's really interesting about this next slide is the hardware. When we look at the physical hardware, it basically comes down to a trade-off between signal quality and surgical risk. On one end, you've got invasive systems that place electrodes directly into the brain's cortex. The signal resolution there is amazing, but obviously it requires major high-risk surgery. On the completely opposite end are non-invasive systems, like EEGs you wear on your scalp. Super safe, but the signals have to pass through bone and tissue, so the quality really drops. And right in the middle, we have semi-invasive systems. These sit safely inside the skull, but outside the actual brain tissue, giving you better resolution without piercing the brain. Beyond just the hardware, BCIs are grouped by what they actually do. Passive BCIs just hang out and monitor your mental state, like keeping an eye out to see if a driver is getting too fatigued. Then there are interactive BCIs. These analyze how your brain responds when you focus on something external, like the well-known P300 signal. And finally, you've got active BCIs. This is where the user deliberately generates a neural pattern, like intensely imagining moving their hand, which is called motor imagery, and the system translates that specific thought into a command. But no matter the type, pretty much all BCIs follow 4 specific steps. First up, signal acquisition. Electrodes pick up the electrical chatter from your neurons and turn it into digital data. Step 2 is feature extraction. Algorithms sift through all that noisy neural data to find the meaningful patterns. Step 3, feature translation. Machine learning models translate those patterns into actual computer commands. And the fourth step is output. The command tells the device what to do, which gives feedback back to the user. This creates a loop where the human and the machine adapt to each other over time. It's wild. All right, let's shift gears to part 4, the market and innovators. And spoiler alert, we're seeing exploding growth here. The financial side of this is just massive right now. In 2025, the global BCI market was valued at $240.6 million, with North America gobbling up almost 44% of that share. But look at this projection. It's expected to hit $295.5 million in 2026 and then absolutely skyrocket to $960.8 million by 2034. We are rapidly charging toward $1 billion industry here. To put that in perspective, that growth represents a compound annual growth rate of 15.9%. That is a truly staggering figure. It shows some serious investor confidence and proves that these laboratory medical breakthroughs are viable, scalable, and ready for the real world. And driving all this money are some key innovators. You've got Precision Neuroscience, which has raised about $155 million to build these minimally invasive, high-resolution implants that just sit right on the surface of the brain. Then there's Paradromics. They've pulled in over $53 million to build high-bandwidth systems that can record thousands of neurons at once, specifically designed for patients with severe paralysis. Another massive standout is Ion Brain Neuroelectronics. They've raised roughly $68 million total. That includes a $17 million Series A back in 2021 and a massive $50 million Series B in October 2024, led by IMX Expand. What they're doing is super cool. They're developing these ultra-thin graphene-based therapeutics combined with AI. They don't just want to decode neural activity, they want to precisely modulate it. Their goal is to create adaptive therapies to treat both central and peripheral nervous system disorders like Parkinson's and epilepsy. The potential applications here go in some wildly diverse directions. Someday, BCIs could even enhance the natural abilities of highly skilled professionals. We're talking pilots, surgeons, engineers. They can already be used to detect the emotional states of patients in vegetative or minimally conscious conditions. And, just to prove it's not all serious clinical stuff, fun fact, during the 2022 BCI Game Jam, developers literally created a fully BCI-controlled multiplayer game called Brain Buddies. How cool is that? Bringing it to part 5, ethics, and why this should be a last resort. While multiplayer brain games are undeniably fun, the medical reality carries an immense amount of weight. As LF Dumla Karakulchu points out, from a user's perspective, the very idea of a brain implant can feel deeply unsettling, even frightening. Her philosophy is absolute. Rehabilitation has to aim at restoring a patient's natural abilities and maintaining muscle function first. Only when literally all other options are exhausted should a BCI even be considered as a tool to improve someone's quality of life. So this really means prioritizing a prevention and early care first approach. We see this with companies like Oxyprem, which monitors oxygen to protect newborn brains, or Freox, working on stroke therapies. Then there's Axtiltis Pharma, trying to restore the blood-brain barrier, and Dynamics VR, using automated virtual reality for rehab. The primary goal is always to heal the body naturally before we ever resort to bypassing it with hardware. The big takeaway here is really one of balance. Look, for folks dealing with severe paralysis, head trauma, or neuromuscular disorders, BCIs are incredibly transformational. They offer this immediate, life-changing benefit. They are also super promising for safely operating robots from a distance in hazardous places like mines, disaster zones, or even space. They are genuinely miraculous. But when it comes to everyday medical patients, they must remain a profound, absolute, last resort intervention. Which leaves us staring right at the ethical horizon. The science is proven, the computational power is here, the market is exploding. As our interactions with technology become quite literally as natural as thinking itself, we're faced with a massive societal question. If our thoughts become the ultimate interface, who gets to decide how we use them? It's a fascinating, complex future, and it is being built right now. Thank you so much for exploring the incredible world of brain-computer interfaces with me today. Keep learning, and I'll catch you next time.